Bismillahirrahmanirrahim. My name is Sayyid Ali Murtaza and I am from Chemistry Department. Now I am going to present the part 2 of my presentation. The topic is lithium-ion batteries. So first we start with the assembly. Lithium-ion batteries are assembled in a series of steps which are discussed in this presentation. So let's have a look at the assembly of lithium-ion batteries. Mixing. As you can see the diagram, active materials, conductive auxiliary agents, polymer binders, and organic solvents are mixed together to form an electrode slurry. Coating, drying, and calendering. As you can see on the diagram, the electrode slurry is coated to copper and aluminum foil, dried and calendared. Slitting. Here you can see that the electrode sheets are slit to each battery size. Winding or stacking. As you can see the diagram, a separator is inserted between the anode and cathode electrode sheets, and the electrode sheets are wound or stacked together. Tab welding. Here's the diagram of the tab welding. The tabs of the layered electrode sheets are welded together and collectors are welded to the tabs. Here you can see the diagram of assembly. Case closing. Here you can see that the covers and collectors are welded together before filling diagram. Electrolyte filling. Here you can see that the electrolyte is filled via the electrolyte port. After filling, you can see that the electrolyte port is closed. Pre-charging. Following electrolyte fill, a charging current is fed to the cells for the first time. Charging and discharging. Here you can see at the diagram, cells are repeatedly charged and discharged. Aging. You can see that the cells are stored for a certain period of time. Coating technologies. The surface coating is closely related to the performance of cathode materials, and various coating technologies could influence the properties of cathode. A thicker coating layer may provide better protection for the particles. Chemical vapor disposition (CVD). In the beginning, the gaseous or liquid reactant containing the desired deposition element and other gases atmosphere required for the reaction is introduced into the reaction chamber. Then a desired solid state membrane material will be deposited on the surface by heating the solid substrate through a specific chemical reaction with mixed vapor. This method is mainly used to deposit carbon-based materials on the surface of cathode materials. Atomic layer deposition. The atomic layer deposition as a popular technology requires a few amounts of precursors and can accurately control the thickness of coating layers, which would assist the fast diffusion of lithium at the internal of the cell. This method provides through covering. However, the electrically conductive pathways can be disrupted, which causes of slowing down the associated charge transfer kinetics. Radio frequency magnetron sputtering. The RF magnetron sputtering is a technique where argon ions are accelerated by an RF electric field to hit a target made of the material to sputter. The target is sputtered in all directions. In particular, the sputtered atoms will reach the substrate placed in front of the target, but outside of the plasma to prevent etching by the plasma. The major feature of RF sputtering is that the sputtered material is coated mainly on the outer surface of the composite electrode, and this technique has a faster growth rate than ALD. Organic pyrolysis technology. This technology needs mixing the organic coating material with the cathode material or the raw material for the synthesis of the cathode material, and then high temperature treatment will be endured. Organic pyrolysis is mainly employed for the carbon coating on the surface of the cathode material to form a core shell structure by carbonization of the organic substance. Organic substances are commonly used as carbon sources, including sugars, glucose, sucrose, polymers, phenolic resin, polyethylene glycol, polyvinyl alcohol, polyvinyl butyryl, polyacrylate, etc., and asphalt, AT. Co-precipitation coating. Precipitating agents will be added to the solution to forming a coating on cathode material particles by precipitation followed by heat treatment. This method has been widely used to form coatings such as oxides, phosphates, and fluorides. Coating materials. Oxide. As a typical coating material, oxides have been widely exploited in the surface modification for cathode materials of LIB. The coating oxides include MgO, Al2O3, SiO2, TiO2, ZNO, ZRO2, CEO2, and RuO2, etc. Among them, MgO, Al2O3, and TiO2 were the most commonly applied for surface coating. Fluoride. Fluoride is also one of the widely used coating material for modifying the surface of cathode materials. A key factor of the electrochemical performance degradation in LIBs is that the commonly used electrolyte LiPF6 will produce highly corrosive hydrofluoric acid during operation of the cell, which leads to the dissolution of active materials in the cathode. Therefore, an important method to increase the capacity retention of LiB is to reduce the dissolution of active materials in the cathode. Such problems can be solved by utilizing fluoride coated cathode. On the one hand, the common electrolyte in LiBs is LiPF6 F/ can effectively inhibit the occurrence of interfacial side effects. On the other hand, it is found that the addition of F/ can reduce the charge transfer resistance, improve the conductivity, and thus improve the rate performance and cyclability of the cathode material. The typical fluorides as surface coating include LiF, MgF2, AlF3, CaF2, YF3, and LaF3. Lithium containing composite. Apart from the oxide and fluoride coating, the lithium containing composite has also received much attention on surface modification. At present, this type of materials is mainly lithium containing composite oxide, including LiAlO2, Li2Si2, O5, Li2TiO3, and Li2ZrO3. LiAlO2 has excellent high temperature stability and is chemically inert in the organic electrolyte, which can inhibit side reactions at the interfaces of the electrode or electrolyte and improve the structural and thermal stability of the cathode. In addition, lithium in the lithium aluminum oxide may partially occupy the position of lithium in cathode material, led to a good lithium-ion conductivity, which resolves the lithium transmission problem at a high current rate and enhances the high rate performance of the battery. Phosphate. Because the chemical bonds between PO43 group and metal ions in the phosphates have strong covalency property, it will hinder the reaction between the electrode and the electrolyte after the coated cathode material, which improves the stability of the material. Currently, the development of phosphates on surface coating mainly involves FePO4, AlPO4, and CO3PO4 MnPO4 coated NCM622 offered a remarkable stability after 100 cycles at higher testing temperatures. The capacity retention was 94% at 40 degree centigrade and 83.1% at 60 degree centigrade respectively. These values were much higher than those for uncoated NCM622, which retained only 87.6% at 40 degree centigrade and 68.8% at 60 degree centigrade. Lithium solar batteries. Lithium solar batteries are simply lithium batteries used in a solar power system. More specifically, most lithium solar batteries are deep cycle lithium iron phosphate batteries, similar to the traditional lead acid deep cycle starting batteries found in cars. LiFePO4 batteries use lithium salts to produce an incredibly efficient and long-lasting battery. Because these batteries are deep cycle batteries, they are great for solar applications which experience irregular charging and discharging. Are lithium solar batteries really the best for solar panels? Yes. Lithium solar batteries outperform the competition when it comes to storing energy for a solar system. They are more efficient, charge faster, require no maintenance, and last substantially longer. The efficiency comes from the very low internal resistance that allows the batteries to charge with minimal loss. This also means that they can discharge with minimal loss. So, the energy in equals the energy out. When charging less efficient batteries, any loss is lost solar energy you cannot recover. When you factor in these benefits, lithium solar batteries are a more cost effective option than other battery types in a long run, despite their premium price tag. Great for inconsistent solar charge cycles. Solar charging conditions can be inconsistent as a result of weather, location, and time of year. Charging can vary significantly from one moment to the next, and cloudy days can practically render a solar array useless. Inconsistent charging may damage lead acid batteries, but this is not an issue for lithium batteries. Lifespan beyond 5,000 cycles. One of the most important aspects to consider is how long they last. Typical lead acid batteries can last anywhere from 200 to 900 charging cycles. Under ideal conditions, with proper maintenance, this ends up being a few years at the most with daily solar charging. How does lithium-ion battery works? Sunlight hits the solar panels and the energy is converted to DC electricity. The electricity enters the lithium-ion battery and is stored as DC electricity. The DC electricity then leaves the lithium-ion battery and enters an inverter to be converted into AC electricity the home can use. Environmental impacts of lithium-ion batteries. Lithium environmental advantages. Renewable energy sources. Lithium-ion batteries can store energy from renewable resources such as solar, wind, tidal currents, biofuels, and hydropower. Using renewable energy means we get fuel for our cities and homes from sources that are naturally replenished and create fewer carbon emissions than fossil fuels. Resilience, stored energy as with battery systems can be beneficial in the case of disasters that threaten the power supply. Having reserved energy in portable containers helps us to be resilient, able to recover from unfortunate circumstances such as natural disasters. Drawbacks, open pit mining. In order to make way for an open pit, vegetation must be cleared way. Then a deep pit is dug. Together, these factors create conditions for erosion. Mining can create toxic soils and dust with high concentrations of heavy metals. These dusts become contaminants that put people and animals at a higher risk of illness. Brine extraction. Brine extraction drains water from natural underground reserves of drinking water. This water is depleted from the ecosystem more quickly than it can be replaced through the water cycle. Brine extraction also requires toxic chemicals to process lithium. The release of these chemicals harms air, soil, and water quality. Anode chemistries, carbon-based anode materials. Carbon is one of the most attractive elements of periodic table because of its large natural abundance and unique properties. The carbon exists in various forms, from crystalline to amorphous as well as in different shapes such as OD fullness. 1D carbon nanotubes, 2D graphene sheets, which also can be assembled into 3D networks. Similarly, the properties of carbon also vary with its nature or shape and can be tuned according to the specific applications. The existence of special chemical nature of carbon atoms in graphic form made carbon-based materials most attractive candidates for EES systems. Presently, the anode of commercial LIBs is primarily made of graphite, but its limited theoretical capacity is a major drawback associated with graphite-based LIBs. Alloy-based anode materials. Alloy-forming compounds fall in the category of high theoretical capacity anode materials, for example, silicon, germanium, SN, etc., with capacity values of 4200 mAhg, 1600 mAhg1, 999 mAhg1, respectively, through an alloying product of Li44M. The larger capacity of Si than other alloying materials is based on its smaller atomic mass while they form same alloying product. Thus, it is believed that these materials will result high enhancement in the overall energy density of LIBs and make them eligible for EVs. Cathode chemistries. Oxide cathode investigated is the layered LiCOO 2, in which the monovalent lithium and trivalent cobalt ions are ordered on the alternate planes of the rock salt structure with the cubic closed array of oxide ions 12. This structure is referred to as the ozone structure. The large charge and size differences between lithium and cobalt ions led to good cation ordering, which is critical to support fast two-dimensional lithium-ion diffusion and conductivity in the lithium plane. The good structural stability along with high electrical and lithium-ion conductivity offers fast charge discharge characteristics with good reversibility. With these features, LiCOO2 remains on one of the best cathodes to date with a high operating voltage of approximately 4 volt. As you can see the diagram of cathode chemistries. Cathode class 2, spinel oxide, the stable Mn216DO4 framework with edge shared octahedra offers a three-dimensional lithium-ion diffusion pathway with fast lithium-ion conductivity. The lithium-ion conduction occurs from one 8A tetrahedral side to another 8A tetrahedral side via a neighboring empty 16C octahedral side as it offers the lowest energy barrier. The good three-dimensional structural stability along with high electrical and lithium-ion conductivity offers even faster charge discharge characteristics for Li1 XMN2O4 with good reversibility compared to LiCOO2. The insertion or extraction of lithium into or from the tetrahedral sides with the deep side energy in Li1 XMN2O4 offers a high operating voltage of 4 volt with a practical capacity of smaller than 130 mAhg1 as close to 1 lithium per 2 Mn ions can be reversibly extracted from the tetrahedral sides. As you can see the diagram. Separator chemistry. Conventional lithium-ion battery separators are microporous polyolefin membranes that play a passive role in the electrochemical cell. Next generation separators should offer significant performance enhancements while being fabricated through facile low-cost approaches with the ability to ready tune physicochemical properties. This study presents a single-step manufacturing technique based on UV-initiated polymerization induced phase separation, wherein microporous separators are fabricated from multifunctional monomers and ethylene carbonate, which functions as both the pore-forming agent and electrolyte component in the electrochemical cell. By controlling the ratio of the 1,4-butane diol diacrylate monomer to ethylene carbonate, monolithic microporous membranes are readily prepared with 25 μm thickness and pore sizes and porosities ranging from 6.8 to 22 nanometer and 15.4% to 38.5% respectively, with 38.5% apparently porosity and average pore size of 22 nanometer. The poly the poly 1,4-butane diol diacrylate separator takes up the PBDDA separators were shown to be thermally stable to 374 degree centigrade, lacked low temperature thermal transitions that can compromise cell safety and exhibit no thermal shrinkage up to 150 degree centigrade. Here you can see the diagram. What batteries are Tesla using in its electrical cars? All of Tesla's traction batteries are lithium-ion batteries, but they are not all the same. There are several main cathode chemistries, each of which evolves over the years. The three main cathode types in Tesla's EVs: nickel, cobalt, aluminum, nickel, cobalt, manganese, lithium-ion, lithium iron phosphate. The two first, NCA and NCM, have a high energy density, which, which predisposes them to use in long-range variants of Tesla cars. Those two types were used in cylindrical cells, NCA in 1865 and 2170 from Panasonic, NCM in 2170 from LGES. Here you can see the diagram of nickel cobalt aluminum cathode, nickel manganese cobalt cathode, lithium iron phosphate cathode. The LFP is a less energy dense type. It does not contain any nickel or cobalt, which makes it less expensive. It's a perfect fit for entry level models and the energy storage system. Tesla uses prismatic LFP cells from CATL. In the recent 2021 impact report, the Tesla explains that it will continue to advance a diversified cathode strategy for LFP, nickel-rich and manganese-rich cathodes to address various market segments for vehicle and energy storage products and provide future flexibility based on raw materials availability and pricing. Tesla tries to increase nickel content and reduce the cobalt content in NCA and NCM batteries, which would reduce the cost and improve energy density. However, it's not easy to remove cobalt because of its role in the safety and longevity of the battery. The company also notes that in the coming years, its absolute cobalt demand will increase because the production growth of batteries and vehicles is forecasted to outpace the overall rate of cobalt reduction on a per cell basis. We must also remember that the cathode is not the only element of the battery, and there are constant improvements to all elements, including the anode, silicon versus graphite content, and the electrolyte. Finally, the battery suppliers initially and for a long time, Tesla's primary battery supplier happened to be Panasonic in 1865 and 2170 type cells with NCA chemistry, but later it was joined by LG Energy Solution and CATL. On top of that, Tesla has started its own battery production, the 4680 type cell with undisclosed chemistry. Tesla's 1 millionth cell was produced in California in January. An electric car might need up to about 1000 such cells. Thank you.